So chapter 7 is all about energy. Energy is the ability to do work. It could be actually work that's taking place, and when we say work, we mean a physics version of that. Supplying heat is one kind of work. Moving an object is another kind of work. And we can really break it down into potential energy, that is energy that is stored due to its position somehow, that is not actually supplying work at a given time, but has the potential to supply the work. Or kinetic energy, which is the energy of motion, which is an actuality, what's happening. So again, we're focusing not so much on balls that are at the top of the hill. And in physics class and in physical science, you tend to talk about gravitational potential energy and maybe elastic potential energy. But when we're talking about potential energy, we're talking about the energy that is stored by holding two particles that are attracted at a distance from one another. So our location is really talking about the distance between the particles when we're talking about chemistry. And kinetic energy, when we talk about moving the objects are particles. And so we're mostly going to be focusing on temperature as our version of kinetic energy. In physics class, you get into a lot of other kinds. A couple of things we want to get out of the way is we need to be clear on what the units of energy are. The common unit of energy in science is usually the joule, use capital J, and sometimes based on size we might use kilojoules if we have a lot of energy, and that's just using the kilo prefix. And to get an idea of what size a joule is, if you lift a 1 kilogram mass to 1 meter above the floor in 1 second, that takes 10 joules. So that's not very much energy, but it adds up. And another common unit that we use a lot of times is calories. That's the British unit. And a 1 calorie is equal to 4.184 joules. So we can always use conversions to be able to convert back and forth between calories and joules. Now, we won't get into nutritional calories, but we call things, oh, this has so many calories in it. Usually when we're talking about nutritional calories in food, we're really meaning 1 kilocalorie of energy. And they differentiate it by capitalizing the C and calling it calories with a capital C. So that's just something to be aware of if you're doing anything with nutritional work. Also, we're going to deal with temperature a lot. Again, temperature has some relationship to the kinetic energy of a sample, so it ends up being involved. Just reminding you, we've talked a little bit about temperature conversions before, but you need to be able to convert Fahrenheit to Celsius and back and forth, and also Celsius into Kelvin. Kelvin is our absolute temperature that we use in chemistry most often. In this unit, we'll be able to use a lot of degrees Celsius. When we move into chapter 8 and talk about gases, you have to use Kelvin. So that's important to be able to convert back and forth between Kelvin and Fahrenheit. Kelvin is degrees Celsius. So just to get a kind of reference for potential energy, what's going on with a lot of potential energy in matter is it's present because particles are weakly attracted to each other. So if you have two neutral atoms, they are weakly attracted to each other. All mass is attracted to each other. That's what gravity really is. It's just that it's such a weak force that you need to have something with a lot of mass before it's usually apparent. But also oppositely charged particles are attracted to one another. And when you have particles that are attracted to one another kept apart, there is the potential to move together. Therefore, as we keep them a distance apart, that's a form of stored potential energy. And when they are brought closer together, they would have less potential energy. So far apart, moving to closer together would be releasing energy in the form of some kind of potential energy. So for like charged particles, of course, which are repulsive, the direction is opposite. There's less potential energy when they're far apart than when they're closer together. So within matter, again, typically in physical science and in physics class, we talk about potential energy in terms of a ball at the top of a hill. That's really referring to gravitational potential energy, or a stretched rubber band. That's really referring to elastic potential energy. But in matter, we're talking about these two atoms. So the way we see this show up in chemistry is 3 different ways. The state. So remember that solids are particles that are held closely together and they have a lot of attraction for one another. Liquids have a little less attraction for one another. They're slightly further apart and they move a little bit more freely, and gases move very freely and have no attraction or pretty close to no attraction. So when we change state, we are changing that potential energy, and therefore that is one way that we'll see potential energy converted into kinetic energy. Another form is chemical bonds. So unbonded particles have a higher potential energy than bonded particles. And we have also moving electrons. Again, electrons are negatively charged and protons in the nucleus are positively charged. So that's an attractive set of particles. And as you move the electrons to further distances, you're going to have more potential energy. So that's another form of energy that we see in matter. Kinetic energy, on the other hand, is the energy of motion. And of course, particles are in movement at all times. Atoms are always moving. They're in constant motion. And so within that, how they're moving, and we can actually have within a molecule, there's other forms of motion, vibrational and rotational. But those are all forms of kinetic energy. And the movement of a atom is actually related to the temperature of the sample. So a hot sample has more kinetic energy than a cold sample. So we can think about those ways that we'll see energy in matter. However, chemists like to sort of change things up a little bit. Let's remind you about the fact that energy is conserved. So it cannot be created nor destroyed. So what we're going to be studying in chemistry is not creating energy or destroying energy, but rather moving energy from one location to another location. So the transfer of energy can cause energy changes in matter, and now I'm going to be involving the surroundings and the system. So we're going to sort of, instead of talking mostly about kinetic and potential energy, we're going to focus on something called internal energy. And we're focusing on two general ways that I can change the energy of matter using outside. If I add energy to a system of matter, how might it change the energy in that system? And the increase in internal energy of a system we'll call delta E. Delta in general means a change between two states. So it was at one energy, I'm going to increase it to a higher level of energy. It can be done two ways. One, it can be done from heat energy given to the system, and it can be done by work energy done to the system. So Q stands for heat energy and work, and W stands for work energy, and these are both things that are given to the system. And since energy is conserved, the only way the energy can increase is for the system to be given energy from its surroundings. It can't just make it up. One of the big things that gets confusing is that we need to sort of break up and talk about the chemical system and its surroundings. And you can get easily confused here because some of the things we like to think of as being part of the system when it's really not. It's part of the surroundings. So the chemical system itself is the actual chemicals undergoing a chemical reaction or a physical change. They're the starting materials as well as the new materials formed, but it's just those chemicals. Things that are just nearby, like the container, the thermometers, also the water. If it's in a solution, the water that it's in is not part of the reaction. It's just sort of part of the surroundings. So those things are where we can get the energy from or where the system can transfer energy to. And signs become incredibly important in this chapter and very confusing. So the sign of delta E, Q, W, delta H, we'll talk about enthalpy later on, entropy, delta S, any energy quantity refers to the direction of the energy transfer. So if I have a positive value, it's implying that the surroundings are transferring energy to the chemical system, and the system is increasing in some kind of energy. And we'll use the prefix of endo when it's a positive energy transfer. A negative means that the system is transferring energy to the surroundings. So the chemical system is actually decreasing in energy and transferring that to whatever else is nearby. Also, we can think of extra words in the word problems as being sort of a double negative. If the wording, so the definition of delta E is how much energy is the system increasing by. Therefore, if I asked how much energy is released by the system, I'm really asking for the negative of what the quantity delta E is. And if delta E itself is negative, the negative of a negative is a positive. So if the energy change is negative and the question has worded it in such a way to say how much energy is released, we would want to enter a positive number. And that can be pretty confusing, I understand. So again, some vocabulary. When we say exothermic, we're referring to the fact that the system is releasing heat to its surroundings. Exergonic is saying that the surface is releasing energy to the surroundings, but it's not necessarily heat energy, only partially. Endothermic means that the system is absorbing heat from the surroundings, and endergonic means the system is absorbing energy from the surroundings, but it's not saying which type. So when we see heat in working chemistry, we end up seeing heat in terms of three different processes that can happen. Particles getting hotter means that the system is increasing in heat. Samples melting or boiling means that the system is increasing in heat energy. Or if it is breaking bonds, and if I do the opposite process, if I cool, that's a heat releasing process. If I freeze or condense and do those state changes are releasing heat processes, and making bonds is releasing heat processes. I also have work processes. Now work, when we talk about physics, means a force acting on an object over a distance, and it's the energy related to that process. So it's actually calculated as a force times a distance. And if I have matter that can apply a force over a distance, then I can have work energy involved in chemistry as well. And that's typically going to happen when we're dealing with gases. So if a gas is applying it applies pressure, which is force per unit area, to a surface over a given area, that is a form of work being applied. So depending on the system could have gases that are applying work, applying a force to the surroundings, and the surroundings could have gases that are applying a force to the system. Other than talking about the fact that this is involving pressure and volume, we're not going to really get into work in this semester. We'll skip that topic. We will discuss it generically, but we won't do calculations referring to work. So then for the heat problems, the three types of heat problems we're going to see, if I want to calculate the heat change that occurs when a sample raises in temperature, that would be a physical change, but a system of matter can raise in temperature. I have the equation Q stands for heat, is equal to the quantity, I'm using N for moles, but it sometimes is mass, times Cp, which is a specific heat, times the delta temperature, the rise in temperature. And we'll talk more about these equations in specific, but I'm just kind of giving you an overview. If I want to melt or boil, they have very similar equations. It's going to be equal to the mass times a constant. For melting, it's called the heat of fusion constant, and for boiling, it's called the heat of vaporization constant. And for chemical reactions, I have the quantity in the system times something called the enthalpy, the change in the enthalpy of reaction. I do have to worry about coefficients there, and we'll talk about that one later on in the chapter. Now you notice that I don't have equations listed for decreasing in temperature or for freezing or for condensing, and that's because cooling temperature is just the negative energy process of raising in temperature, and freezing and condensing are just the negative energy process of melting and boiling. So I would simply adjust those equations by putting a negative sign in front. In chemical reactions, the sign of whether it's increasing or decreasing, is built into the delta H of reaction. And if I have more than one process going on, I can calculate the heat for each process and add them together. I do want to point out that heat and temperature are not the same thing. Temperature is not equal to heat. And unfortunately, you probably will easily confuse the two, because if I say, oh, heat that or warm that, you think that they mean the same thing. But in science, the words heat and the words warm mean two different things. The word heat means heat energy is being transferred into whatever it is you're talking about. If I want to heat some potatoes, I'm applying heat to those potatoes. If I warm them, it's saying the process of changing the temperature and increasing the temperature. So they mean two different things. And I want to be careful, because when I apply heat energy, although it often does result in a temperature change, that's not the only thing that can happen. It can also result in a phase change or a chemical change. And so I have to be clear that it's not necessarily going to, applying heat to a chemical system often results in a temperature increase, but not always. Another fact that I do need to know about heat energy is that the conditions for transferring heat energy from one thing to another, like the surroundings to the system or from the system to the surroundings, it's always going to flow from the warmer object to the colder object until both objects reach a thermal equilibrium. So the direction is determined by the relative temperatures of the surroundings and the system, and it will keep flowing heat energy until it reaches thermal equilibrium and both are at the same final temperature. And that becomes important later on when we're going to do some calorimetry. The last question that we really want to get involved in before we really start working into specific heat types of problems is, how do I know when I apply heat whether it's going to change the state or whether it's going to change the temperature? Usually if it's going to instigate a chemical reaction, or if a chemical reaction is causing heat to be released, there'll be some information. But sometimes in a heat problem you have to decide which type of heat process is this. And it really depends on what is the temperature. Melting and boiling can only occur at very specific temperatures. Melting can only occur at the melting point of the substance, and boiling can only occur at the boiling point of the substance. And when it is melting or when it is boiling, notice that the temperature does not change. All of the heat energy be given to a substance when it melts is going into the state change, and none of it is going into changing the temperature. In between the melting point and the boiling point, or below the melting point or above the boiling point, I can have heat going into changing the temperature of the samples. And so that's how you decide which of the processes you should be using and which equation.